Chapter 4, Note C, ends with the concept of formal charge. I've pulled this out as a separate video because I actually think this is a super important concept. You may want to review this video once you get to college. It's definitely a big deal in college. That being said, you're not going to have a specific question on what is the formal charge of a certain atom on your IB test. It is, however, part of the AP tests. So if you're self-studying for the AP test, you definitely need to know about formal charge, and you definitely need to know about it in college. As far as IB goes, they do expect you to determine the correct structures of molecules. There just won't be a specific question on what is the formal charge. Funny part is, the only way to determine the correct structure is to look at the formal charge. So, long story short, you need to know this. There's a very straightforward formula to determine the formula charge of an atom. First, you would look at the number of valence electrons that atom would have. This is the number based on its location in the periodic table. For example, hydrogen as an alkali metal would only have one valence electron, whereas carbon in group 4 would have 4 valence electrons. So it's all just based on where they are, how many valence electrons are in their outermost shell. We're going to compare that to how many valence electrons they actually end up with in the structure. So this is going to be the total of the lone pairs plus 1 electron from every bonded pair. So we're kind of going to split the bond in half and let each atom claim one of those electrons, and then you add that to the lone pairs and you get your second number. And overall, we're going to subtract. We're going to find the difference between how many electrons it would have on the periodic table and how many it actually ends up with. Let's look at some important things concerning formal charge. The first bullet point here is just the long version of that formula that we just looked at and how to determine the formal charge. Why do we need the formal charge? Well, first of all, the formal charge of every atom in the molecule must equal the overall charge of that molecule. So if we're looking at a polyatomic ion, the formal charge of each atom should equal the charge of the polyatomic ion. And if you're looking at a molecule that's neutral, the formal charges should cancel out overall. Now, about the polyatomic ion, if there is a charge, keep in mind that that charge would be delocalized over the entire molecule. The other reason we really need formal charge, and this is the part that IB really cares about, is that the formal charge would be closest to 0 in the molecule that is the most stable. So if something has a formal charge that ends up to something further from 0, and there's a more stable option, only the more stable option would exist in real life. We're going to look at a couple examples. First, let's look at a molecule you should be very familiar with, carbon dioxide. You probably recognize the left structure as being the correct structure, the one that we have always used for carbon dioxide. But the structure on the right actually does meet all of the requirements of a valid Lewis structure. Every atom has access to 8 electrons, and we have used exactly the number of valence electrons that carbon and oxygen brought in. These structures both meet the requirements of a valid Lewis structure. So why does only the left structure exist in real life? And the answer is, of course, its formal charge. So let's go through and find the formal charge of every atom in these molecules. First, let's record the number of valence electrons for each atom. We know oxygen is in the 6th column, so it would have 6 valence electrons, and carbon is in the 4th column, so it would have 4 valence electrons. And again, this is the valence electron of the atom as it exists unbonded. The next thing that I want to look at is how many electrons the atom actually has access to, how many electrons the atom actually has access to in the structure. So for my very first oxygen, we have 2 lone pairs, and we would count 1 electron from each of the bonds. So that would be a total of 1, 2, 3, 4, 5, 6. 6 electrons that it has access to. For carbon, it would have access to 1 electron from each bond. So since it has 4 bonds, that would be access to 4 electrons. Then for our other oxygen, we again would have access to 1 electron from each bond. We're up to 2, 3, 4, 5, 6 from our lone pairs, 6 electrons. And if you do this subtraction here, of course, 6 minus 6 is 0, 4 minus 4 is 0, and 6 minus 6 is 0. So the formal charge of a balanced carbon dioxide is 0 across the board. Now let's look at the other structure and see how the formal charge is not ideal. So first let's count the electrons on our first oxygen. We're over on the right-hand molecule. We have 6 electrons in the lone pairs plus 1 of the electrons in the bond. That's a total of 7 electrons. Carbon has access to 1 for each bond, so 1 from the single bond and 1 of each of the 3. So carbon actually still has 4 for its assigned number. And then for oxygen, it would have also 3 electrons from the triple bond, and then the other 2 from the lone pair. So that's actually 5 electrons. Doing this math does not yield 0 across the board, of course. 6 minus 7 is a -1. The 4s are still 0. And then 6 minus 5 is a +1. Notice that +1 and -1 do cancel out, so it still gives the neutral molecule. But given the choice between a formal charge that has positive and negative ones and something that's 0 across the board, only the balanced molecule, the more stable molecule, would exist. Formal charges can not only help us figure out how to balance the bonding, they can also help us determine the arrangement of the atoms in general. In this example, we're going to look at nitrogen, carbon, and oxygen forming a polyatomic ion. Now here, we could have carbon, nitrogen, or oxygen as a center molecule. You see these structures here as our options. What we need to do in order to figure out which one actually exists is find the formal charge of all 3 versions and see which one is closest to 0. First, let's record the number of valence electrons. Again, just straight off the periodic table. Nitrogen is in the 5th column, so 5 valence electrons. Carbon in the 4th column with 4 valence electrons, and oxygen in the 6th column, so of course 6 valence electrons. But now we want to figure out how many electrons are assigned to the atom when we do the bonding. So looking at nitrogen, we see 2 lone pairs for a total of 4 electrons, and then 1 from each in the double bond. Now we're up to 6 electrons assigned to that nitrogen. Now let's look at carbon. Carbon has a total of 4 bonds, so it would take 1 electron from each of those bonds for a total of 4 electrons assigned to that atom. And last but not least, we'll look at oxygen. We've got 4 electrons in the lone pairs, plus 1 from each of the bond attached between the carbon and the oxygen, so that is a total of 6, meaning we have 6 electrons attached to that oxygen. Now let's do the math. We subtract 5 minus 6, we get a -1. 4 minus 4 is of course 0, and 6 minus 6 is of course 0. Notice that total charge there, -1, represents the charge of the polyatomic ion. The other atoms have completely 0 formal charge, so this seems like a very stable molecule, but let's check out the others. In this version, we have nitrogen in the middle. Again, we're going to start off by determining the valence electrons. So again, for carbon it's 4, nitrogen 5, and oxygen 6. Now let's look at how many atoms are assigned to each, how many electrons are assigned to each atom in this version. So first, starting with the carbon, I have my 4 electrons in the lone pairs, and then 1 from each of the bonds, so that would be a total of 6 for the carbon. Then if we look at the nitrogen, we have 4 total bonds. So on the nitrogen, we would have 1 electron from each bond for a total of 4 electrons assigned to the nitrogen this time. Notice how that's kind of the same as when the carbon was in the middle. It had access to 4. And then when we look at the oxygen, we have the 2 lone pairs and 1 from each bond for a total of 6. So we have 6 for oxygen. This time when we do the math, we don't get so many zeros. 4 minus 6 is a -2. 5 minus 4 is 1. 6 minus 6 is at least 0. Notice the -2 and the +1 still add up to the -1 charge on the polyatomic ion, But this is much more unstable. In general, it is further from 0 overall. So this is not the right structure. Let's look at the third option. In this version, we have oxygen in the middle. Let's again go through with our valence electrons. Carbon has 4 valence electrons, oxygen 6, and nitrogen 5. And here we're going to find a different version of electrons assigned to each atom. This time, when we start with our carbon, we have the 2 lone pairs and 1 from each bond for a total of 6. When we look at the oxygen in the middle this time, it has 1 from each of the 4 bonds for a total of 4. And then the nitrogen would have the 2 lone pairs for 4 electrons and 1 from each bond for a total of 6. So 6 assigned to nitrogen in this case. Now let's do this math. 4 minus 6 is a negative 2. 6 minus 4 is a positive 2. And then 5 minus 6 is a negative 1. So the negative 2 and the positive 2 cancel out, leaving the negative 1 again to represent the charge. This is the worst of all. None of this is close to 0. This is definitely not the right structure. So if we compare the formal charges of each atom in the various structures, shown here in the red numbers above the atoms, you can see the right structure would be the one that is overall closest to 0. Notice though, no matter what we do, it's impossible to get a total formal charge that is different from the polyatomic ion charge of negative 1. In IB, you have to at least be able to select the structure that is most likely. In the AP test and in college, you will also have questions specifically to determine the formal charge of an atom in different situations, different structures. That's our last video on Notes C. The next video will be on Notes D, focusing on intermolecular forces.